Is my screen visible? Good afternoon.
Yes, sir.
Good afternoon, sir.
So what was the last topic? Last topic was, I think,
Process queues.
process queues. Okay. Process memory layout was also over, no?
Process schedulers was done, sir. That's it. Process schedulers and process queues.
Completed, sir.
Okay. So today we will be starting off with various times related to process, and then we will be solving numericals one by one for CPU scheduling. Okay. So if I'm talking about process time, there are various time associated with process. Okay. So there are 6 times which we will be looking into it. The first is arrival time. Second is waiting time. Response time. So once scheduling is over, I will conduct one class test. Okay, once scheduling chapter is over, topic is over, I will conduct one class test. Okay. First time, then we have waiting time, response time, burst time, completion or exit time, and then turnaround time. So these are the 6 times related to process. Various times are arrival time, waiting time, and turnaround. So if we talk about a simple figure, okay, states we can have ready, run, then we can have complete. Okay, so we can have arrow like this. Okay, so over here, this can be referred as a time period. This can be referred as a time period. Okay, if I am talking about this point where this line is there, so at this point I'll call it as arrival time. So the first thing is arrival time. Arrival time. Okay. So it is the time at which process enters into ready queue. That means what? Then we have this time period can be referred as waiting time over here. So now we should define what is waiting time. Okay, waiting time. Waiting time is referred as amount of time by a process waiting in ready queue to ready queue for getting CPU. Okay, and this period is nothing but we call it as burst time. Burst time. So what is burst time? Burst time. Burst time is amount of time required by CPU. Required by not CPU. Required by a process for executing on CPU. Okay. So it is also known as execution or running time. Okay, fine. So now if we then we have completion time or exit time. Completion time or exit time. Okay, so this is point of time at which process completes its execution on CPU. Okay. Then we have turnaround time. So what is turnaround time? This is the total amount of time spent by a process in the system. So when process is in the system, so either it can be in ready or it can be in run state, right? So what is the turnaround time if we have to calculate turnaround time? Turnaround time, okay, is equal to burst time dt TAT dot form plus completion time, that is CT or exit time. Sorry, no. Burst time plus waiting time, WT. Okay. Answer, we have 1, 2, 3, 4, 5, 6 is response time. What is response time? So response time is nothing but is it is the amount of time after which process gets a CPU for the first time after entering ready queue. Okay, so these are the 6 things. So if so, this is the first formula, turnaround time. Now waiting time, WT is our waiting time or waiting time will be equal to PAT minus burst time. Okay. Or what we can have is we can write one more formula. Turnaround time TAT can also be easily done by doing completion time minus arrival time. Is it clear or the times clear?
Excuse me, sir.
Yes.
Sir, completion time and arrival time calculated with the time that is shown on the computer, or is it a specific time zone?
No, this will be completion time. So see, for example, if I go for a Gantt chart, if I am going for FCFS or it depends upon when the process is leaving the CPU. Okay. See, burst time prediction cannot be done. Once the process is completed, then we can have arrival time and exit time. Based on that, we can calculate the burst time.
No, sir. I was asking that completion time and arrival time. So it must be shown as something like 8 p.m. IST or
No,
like.
no, that is see. In generally, we talk about milliseconds or seconds or minutes. Okay, so it is given in time. Say for four, four can be seconds. Four can be it can be seconds. It can be in minutes. It can be in hours. It depends upon what is being given to you in the question.
So can you please give an example of an arrival time? Like just how arrival time will be displayed?
No, arrival time will not be. Yeah. So for that, I need to come to scheduling. Okay.
Okay, sir.
When I will be discussing program, I will discuss all whatever is needed. Okay. Next time going into that only through scheduling algorithms, how we will be calculating it. Okay. So is it clear all these times?
Sir, is response time a subpart of waiting time?
Response time is a part of, yes, you can say that. But your waiting time can increase also, no? So for example, I am getting the CPU for the first time. If during execution, if I move out of ready state to wait state for finishing some IO operation, or I have been blocked, then again my waiting time will be difference. The value will be difference of waiting time and response time. But we can rightly say that yes, response time can be a sub part of waiting time. See, for example, if P1, okay, it has this. This is the burst time: 3 minutes of CPU execution and 2 minutes of IO execution. Okay, so suppose the waiting time CPU waits for 2 milliseconds. Okay, then again it goes for 3 milliseconds for CPU execution. It is in run state. And when it wants IO operation, it will again be in wait state for two amount of time, say 2 milliseconds. So what is the total waiting time? So total waiting time is around 4 milliseconds, but response time will be 2 milliseconds. Is it clear now?
Yes, sir.
The next is CPU scheduling. This happens when we are experiencing a multi-programming environment where we have multiple process in our ready queue. Now, which process will be given to the CPU? That is how is this CPU scheduling is performed by whom? This is performed by the short-term scheduler. what will be the criteria chosen by short-term scheduler to pick a particular job from a ready queue and assign it to CPU? That is what is known as CPU scheduling. Okay. Now, what is the main purpose? So this we are doing that first. The purpose of scheduling algorithm. The purpose is first is the maximize utilization. If I'm talking about maximizing of CPU utilization, CPU should not be idle. Suppose a process, for example, in this scenario, what I was telling, a process has this time. This is C, for example. For example, now C. This is the timeline of. This is the burst time of a process. So this is for CPU. This again it wants IO, and again it wants CPU. Now after 3 say milliseconds, P1 will be going for IO. That means CPU will be idle at this moment of time. So the CPU will not be idle. Some process will be given to CPU that will be decided by the scheduler, okay, short-term scheduler. So that is what is the meaning of maximizing of CPU utilization. Just a minute. Okay, so this is what is CPU utilization. Next is okay, there should be minimum turnaround time, minimum waiting time. Okay, these maximize throughput. Okay, maximize minimum response time, minimum waiting time. There should be minimum TAT, all these things. Okay. Now, if I am talking about scheduling algorithms, okay, the various scheduling algorithms. Next topic is scheduling algorithm. First, we have FCFS, first come, first serve. Okay. Then we have SJF, shortest job first algorithm. This is of two flavors. It can be primitive and it can be non-primitive. When it is in non-primitive mode, we call it as shortest job first. If it is in primitive mode, we call it as SRTF, shortest remaining time first. Okay. And then we have round robin scheduling, which is an extension of FCFS in a different manner, primitive FCFS. Okay. Then we have round robin over here. Priority scheduling. Priority scheduling. And finally, we have HRRN, which stands for highest response ratio next. Highest response ratio. Next, scheduling. The priority scheduling can be primitive, which will have primitive or non-primitive. Higher context, there will be frequent swapping between some uh, block state, block, and like that. Again, block to ready to run like that. There will be so context which will be very high in the primitive. Low context will be high, starvation will be primitive. In non-primitive, starvation will be high. So starvation, what is that? An example. First, we will come first serve. So this algorithm schedules job based on their arrival time. So lesser arrival time, sooner CPU. Okay, but the thing is, this is the most simplest and easy, simple and easy, but it suffers from starvation. Now, for example, in case of a tie means two process has the same arrival time. So we can randomly choose any one, or we can go for process with smaller ID will be executed. Okay. So this can be implemented using queue.
Excuse me, sir.
Yes.
So can you please repeat the tie pointer voice cutout?
Tie. Now see P1, P2. I have P1, P0 arrives at time 0. P1 arrives at time 1. P2 also arrives at time 1. So we have a tie over here. Okay. So in this scenario, what I will do, I will go with process with smaller process ID. P1 as a smaller process ID, I'll go for P1. Or I can go for randomly. I can choose P2, then I can go P1. But generally, we can do like this. We can go for process with smaller process ID. Is it clear now? What is type scenario?
Yes, sir.
So there is a convoy effect over here. Convoy effect, which suffers, convoy effect, which will be leading to starvation. So this is an important, these two are some important thing which we need to look into it. Convoy effect and starvation. Now, let us take an example 1.
Sir, please explain starvation a bit, sir.
Not now. With example, I will explain. Okay. In example 3, I will explain you starvation. Is it clear?
Yes, sir.
So say I have 3 columns like this. So here I have process ID, arrival time, and burst time. We have 5 set of process, say P1, P2, P3, P4, P5. Okay. And we have the values, excuse me. First time are 3, arrival time is 3, 5, 0, 5, 4. Okay. This is arrival time and burst time is 4, 3, 2, 1, 3. Now, if I am following FCFS, I need to calculate first average waiting time and average turnaround time. Okay. So for doing this, the first solution is, now how to solve it? The solution is we have to make use of Gantt chart. Okay. Now see how this will be going on. So Gantt chart is nothing but a timeline diagram like this. It will go. Okay. Which will have, this is a timeline. Okay. So at time 0, what we will see? Who is arriving at time 0? P3 is arriving. So this process is arriving at time 0. Okay. Process P1. So we will write P3 over here. What is the burst time of P3? 2. So what happens at 2? See the arrival time. 2 is no. So from 2 to 3, what we will have? We'll have
So CPU will sit idle, sir.
CPU will be idle. Okay, so this will be represented like this. That means there is no process. Now at time 3, what happens? We have process P1, whose burst time is what?
4.
So P1 to 7. 2, 3. Okay. Now by time 7, what happens? P2 has arrived, P4 has arrived, and P5 has arrived. So who will be executed first?
P5.
P5
5.
will be executed. Then we have a tie. Yes or no?
Yes, sir.
Yeah, we have a tie. Now see. So what I will do? I will execute P2. 13. Then I will execute P4.
Before.
P4 is 14. Okay. Is this Gantt chart clear? How to draw Gantt chart? You can write over here also, the bottom also. So either you can write it on the top or write it on the bottom. Both are correct. Okay. So either I can write in the top or I can write it in the bottom. Both are correct. So this box is our, what is this? Ideal time. Yes or no?
Yes, sir.
This is ideal time because we have no process. No process because P3 has completed the execution and no other process has arrived. Okay, so like this, so this is in non-preemptive way. Non-preemptive way means if P3 starts executing, it will finish the execution, then only next process will be aligned. Okay, when the next process gets the CPU, it will finish, then only other process will get the CPU. In preemptive way, what happens? We can stop a running process and move it from running state to block state, and then we can push the new process. Okay. Now let us go to the table. Okay. Now what values we have? We have burst time and we have arrival time. Okay. Now, so we have, now what we will be doing, we will be making our table. Exit time. Exit time of P1 is 7, P2 is 13, P3 is 2, P4 is 14, P5 is 10. So this is your exit time of P1, exit time of P2, exit time of P3, exit time of P4, and exit time of P5. Is it clear?
Yes, sir.
Yes, sir.
Then we have turn around time. So this will be 7 minus 3 is equal to 4. What is 7? Exit time minus arrival time. 7 is your exit time, 3 is your arrival time. Similarly, if I am talking about P2, 13 minus 5. Okay. P3, 2 minus 0. Yes or no? P4, 14 minus 5. P5 will be 10 minus 4. So see, we are getting the arrival time from here. Okay. So we have 8, we have 2, 9 equal
9
to
and
6. Then we have waiting time. So waiting time will be 4.
Oh, boss time.
4 minus 4.
Will be 4 minus 4. Very good. 0. It will be 8 minus 3, 5. 2 minus
2
2,
minus
0.
Oh,
Okay. And over here, this will be
8.
9 minus
minus
1.
9 minus 1, 8. And
8,
6 minus
3.
6,
3.
3.
So next, this table is clear. Now we will be calculating average TAT, right? What was the first question? Okay, sorry. First will be average waiting time. That will be 0 plus 5 plus 0 plus 8 plus 3 divided by 5.
3.27.
So this will be 11, 16. 16 is 3.2. Similarly, average TAT will get it as 4 plus 8 plus 2 plus 9 plus 6. So we have 20, 29 by 5. So we have 29 by 5. That is 5 plus zero point 0.8 unit. This is our this is what we were asked, and this is how we have solved it. Okay, is it clear?
Yes.
Now solve this one. Example 2. This is example 2. Using FCFS, calculate first one, average TAT, average, and we have solve this one. Hmm. 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 So where there is no tie, okay. This will be your Gantt chart. Now draw this table.
So, sir, average waiting time is a 6.2.
Hmm.
And
Okay.
the turnaround time is 12.8, sir.
Turnaround time. Okay. That is 66. I hope so. Total 66 by 5, right?
Yes, sir.
This will be exit time minus arrival time. 0 minus 0, 2 minus 0, 2. Okay. 8 minus 1, 7.